For this first demo, we have chosen the number of passengers through the Vladivostok airport through a number of years and months. So let's load the data. So if you divide your MATLAB code into blocks using this double percent symbol, you can run a single block as we have done here. So let's have a look at the data. So it is a table. It is organized by years. The most recent years are in the first rows, and then they are organized from January to December. So we have reorganized this data into a single vector. So we can see this vector here. So now this vector contains the same information, but now as a column vector. So to do that, what we have done is, well, first you load the data, and then you define an empty vector, and you traverse the table in the right order. So you go from the last rows to the first rows, and then within the rows you take the full row. And then what we have done, this 2 means skip the first column, but the first column was the year that we don't want to take it to make part of the vector of passengers. Okay, so now we have the column vector, so let's have a look at it. So when we plot it as a function of time, and here time starts arbitrarily at 1 and goes to the last month that we have data, and what we see is that in natural units, so this is the absolute number of passengers, we see a growing trend, and we also see that there is a very large variation. So here it goes 10 to the 5, and here it is 10 to the 3. We can see that better in a logarithmic plot. So here we see that it goes up to 10 to the 5, 10 to the 3. So there is a very high variation. The reason for that is that Vladivostok is a Russian city that is at the north of North Korea and Japan. So we can see it here. So it is at the north of North Korea and Japan, and it is very cold in winter. So in December, the number of travelers through this airport drops very dramatically. And we can also see that there is a cyclic trend. So this cyclic trend, this is winter, this is summer, then it goes back to winter, and all summers, the shapes of all summers look more or less the same. Okay, so when there are such large variations in the amplitude of a variable, it is much better to work in a logarithmic scale. So we will do that for the rest of the demo. And in the first model, we will try to explain our the number of passengers now as a multiplier A12, so just a coefficient of what happened 12 months ago. And this is a linear model in the coefficients. So if you go back to your statistical notes, you will see that the solution of a least squares problem with a linear least squares problem is the pseudo inverse of the predictor matrix. So we can let's run this. So we can put the vector of the logarithms of what happened 12 months ago, and then we have it here. We try to predict with that. We try to predict what is the value that we have now, and they have to be of the same shape. So this is the logarithm of the number of passengers now, and then the pseudo inverse gives us beta. So beta in this case is this number. So in the logarithmic scale, there is an increase of about 8% every year. So with respect to what happened 1 year ago, there is an increase of 8% in logarithmic units, 0.8%, sorry. So the R squared is really good, so it is very close to 0.99. That should mean that we are making good predictions, and we can see it here, and they're relatively good. Some of the years they are a bit worse for some unknown reasons. So, and these worse predictions are clearly seen here in the residual plot. So the residual plot goes from minus 0.1 to 0.2, and they necessarily have zero mean, and the standard deviation is whatever. Okay, so let's see if we can do it a bit better. So we now take these residuals and we try to model them. So and to model these residuals, we will use this kind of model. So this kind of model, we have a sinusoid with some amplitude, some phase, and some frequency. So let's see if, because the parameters that we are using, omega and c, they are inside the sinusoid, the problem is no longer linear, so we will need nonlinear fitting, and that is encapsulated here in this MATLAB function. So the predictors now will be n, so n is the time, and what we are trying to predict is E1. E1 is the residuals of the first model. Okay, so let's run it and see. So there is a very nice fitting of the residuals as a function of time. So let's see if we can put both together. So now we will do another fitting, and in this fitting we will include what we know already. So we know that the number of passengers of the logarithm of the number of passengers depends on what happened 12 months ago, and then on a sinusoid, and we put that into a fitting model. So we will use again the fit function of MATLAB because of this nonlinear least squares problem, and then we will use as predictor x. X is what happened 12 months ago, and then we will use here another variable that is time, and then we have this phase. So this new model summarizes or puts together everything that we know so far that makes a good model. So if we run it, these are our predictions. You may remember now that the largest error before was 0.2. If you look at the now it is a little bit smaller, and if you look at the variance, it is smaller. This variance as the other one, and we can know that just in a moment looking at the R squared. We can see also that for the last years the predictions are particularly good. They're not so good typically well here in winter, or here in this year, for instance, when winter ended, the beginning of the number of passengers change a lot, or change with respect to what we expected. Okay, so let's see these, and we can look at the parameters. So the parameters is we already know this 0.7, 0.8 in percent of increase in logarithmic units, and then we have the amplitude. The amplitude is 0.04, so that means 5% of amplitude in logarithmic units. and this minus doesn't matter because it is a sinusoidal function, so this minus translates into a phase term, and then the phase is when the sinusoid should start. We can see now that the r squared is much better than before. Before it was already very good, but this is a little bit better. The reason why the variance, we know that the variance of the residuals is smaller, is because the r squared is the variance of the residuals divided by the variance of the original data, the original observations, logarithm of number of passengers, and then 1 minus that ratio. So because we are closer to 1, we know that the residuals of the second model have to be smaller. And the other thing that we can look at, and this is very interesting, is omega. Omega is the frequency of the sinusoid, and if we compute the inverse of that, this is around 85, and we know that 85, this is in months, so let's put it in months. So every 7 years there is something happening that makes this sinusoid, and maybe this is not something that we can tell whether it will uh, remain in the future, but for the moment, in the last years, this is what we have seen. Then what else? Yeah, we can look at the residuals, the predictions. We can see actually the predictions, you may remember, it is a function of the month. This was in the sinusoid, and it was also a function of the what happened 12 months ago. So that gives us a surface, and this surface, because of the sinusoid, has a, let me see if I can find the right orientation for this to see the sinusoid. It is not easy. Yeah, here you can see a bit, so you can see a bit of the oscillations, and yeah, here you can see. So you have the linear trend because of the of the time. This is the 0.8%, and this is the sinusoidal part. And then what we are doing is explaining our observations as a surface, and a surface on these two variables, time and what happened 12 months ago. And then these blue points are our observations, and here you have the residuals, that the residuals also have a dependence on both variables. Okay, so this is all. So I hope that you can see that with regression you can do very useful explanations of what happened in the past, and hopefully this regression model will also serve into the future, normally into the nearby future, to predict what will happen next, so that you can prepare. If you are the manager, for instance, of the Vladivostok airport, you can prepare what will happen in 5 years from now, and I can do the infrastructure changes so that to accommodate the foreseen number of passengers, for instance. And that is all. See you next time.